Hey, welcome back. In the last concept video, we reviewed computing volumes of solids that were based off of known cross-sections. In this video, we're reviewing the computation of volumes of solids of revolution using the disk method. And like I said, for all volume problems involving known cross-sections, disks, washers, shells, the guideline, it remains the same. And so remember, we will slice, formulate, and integrate in order to receive the appropriate volume. Let's take a look at this curve. Suppose we wanted to revolve the region between the curve and the x-axis around the x-axis to form a solid, and we wanted to compute the volume of that solid. How can we do it? Again, we're going to trust the process. We will simply need to slice, formulate, and integrate. So to begin, let's go ahead and turn this graph. Let's rotate it a little bit, and let's go ahead and see if we can draw some cross sections to see what they look like. What we should be noticing is that all of the cross sections are similar because each point on the curve is being revolved. So notice that each cross section is a circle, and since we're multiplying by an infinitely thin width, this is called a disk, which is why it's called the disk method. So remember, we just need to make a general formula for the area of each cross section, and then we'll need to integrate through our bounds to receive the volume. The great thing is, we already know what the area of a circle is. Each cross-sectional area will be pi multiplied by the radius squared. And the only question left to answer is, what's our radius? We should be able to notice that the radius begins at our axis of revolution. And the radius will be the distance from that axis of revolution to our curve. Or more specifically, r equals the distance from f of x and our axis. Our f of x, well, that is f of x. And we will subtract whatever it is our axis is. Our axis is the x-axis, which means it's y equals 0. So it will be f of x minus 0. We want to practice this very early on. We could be rotating around an axis that is not the x-axis or y-axis. So we do need to be very, very careful when we state our radius. Our radius will not always be f of x. So just keep that in mind. And I'll be sure to show you plenty of example videos moving forward. And since the x-axis lies at y equals 0, our radius in this problem will simply be f of x. And that's only for this problem, so be very careful there. And so now we can go ahead and replace that radius back into our area formula. Because remember, the area of a circle is pi r squared. And so our new area, so our area function written in terms of x, we will have pi times our radius, which is f of x minus 0 squared. And there we go. And so our area of each cross section will be the area is pi times f of x squared. And now we'll just need to integrate as follows. We'll be computing the definite integral from our lower to upper bound, a and b, and we'll just simply input our area function in terms of x, and we will be integrating with respect to x. So upon replacing everything, we're going to have the definite integral from a to b of our area function, which we saw was pi multiplied by our radius squared. So f of x all squared. And then we are going ahead and taking each one of these circles, multiplying it by dx, or that differential of x, which makes each one a disk, a very, very thin disk. And then so the definite integral from a to b adds up all of those very, very thin disks and will give us the volume of this solid. One thing I do want to point out is that we can definitely look at this constant pi and then pull it out of the integral, leaving us with pi multiplied by the definite integral from a to b of f of x all squared with respect to x. Just like that. And so to recap, to compute the volume of a solid of revolution on an axis, we need to compute the following, just like with any problem involving a volume based on cross sections. We will go ahead and compute our definite integral from our lower to upper bound, and then we will be integrating. So our integrand will be the area of a cross section as a function of x, and then we will be computing this integral with respect to x. In the case of the disk method, the area of each cross section will be as follows. The area in terms of x will be pi multiplied by our radius squared. That will be the area of each known cross section. The only question lies in making sure that the radius is written in terms of x, because that is what our area needs to be in terms of in order to integrate with respect to the same variable. So keep that in mind. Next, when we compute that radius, remember that the radius is equal to the distance between our function and our axis of revolution. So more importantly, it will be f of x minus our axis. And I'm just going to go ahead and state axis right there. I don't really want to use a variable name for this. I just want you to understand that we are taking the distance between f of x and the axis. And to be very clear, it doesn't matter if we include axis minus f of x or f of x minus axis. It really doesn't matter because we are squaring this. We are squaring this. So it doesn't matter which one comes first because we're squaring it to get the same positive answer anyway. For example, if we did 1 minus 2 all squared as opposed to 2 minus 1 all squared, we'd receive the same answer because 1 minus 2 squared is negative 1 squared, which leaves us with 1. And let me go ahead and make sure we have a parentheses around that negative 1. If we had 2 minus 1 squared, hey, that'd be 1 squared, which again gives us 1. So this is what I mean. It doesn't matter which way we write r, we're just computing the difference or the distance between our axis and our function. So once we have that out, then we can go ahead and just replace our function with the integral. So we would just be integrating a to b, and I always like to make sure to put the pi on the outside. So this is the finalized formula. I would have that pi on the outside, and then I'm going to go ahead and take the difference between my function and axis, then proudly square it and multiply it by dx. And again, dx is just that marker for the integrand. We're taking the integral with respect to x, but we always want to think about it as that very, very tiny width of each cross section, making it a solid, a very small solid that we're adding up together with the others. And that's it. In the example videos, I assure you that I'll work out all possibilities so you can see every situation and axis that we can revolve around. So go ahead and practice, and then check out those videos for the examples if you get stuck. If you work to understand the disk method, I promise you, you'll have no trouble grasping the washer method because it's just an extension of the disk method. When we computed areas between curves, did you remember that we computed the upper area and then subtracted from it the lower area to receive the area between the two curves? The idea translates to volumes by hollow solids, which is the washer method. So go ahead and get to practicing, and I'll catch you in the next concept video. Have fun.